Ujú.
alrededor
¿Así
de...
verían mis diapositivas?
Ya se ve.
Vale, perfecto.
Bienvenidos nuevamente al Seminario de Búsqueda de Nueva Física en Aceleradores y el Cosmos. El día de hoy contamos con la presencia del doctor Rogermorales. Jonathan nos va a hacer el favor de dar una breve introducción del investigador. Entonces, adelante, por favor, Jonathan.
Sí, bueno, buenas tardes. Tenemos el honor de tener hoy en día con nosotros a Roger Morales, al doctor Roger Morales. Él hizo su licenciatura en la Universidad Autónoma de Barcelona de 2015 a 2019. Posteriormente hizo su maestría, ¿no?, en el Bohr Institute, que está en Copenhague, Dinamarca. Y ahí también continuó su doctorado, ¿no?, con Matthias Willem, trabajando, ¿no?, estos temas, ¿no?, de integrales de Feynman, ¿no?, y estudiando, ¿no?, las geometrías, ¿no?, que hay detrás de todas ellas. Bueno, hace como un año también lo tuvimos aquí de invitado, ¿no? Casi exactamente hace un año, ¿no?
Sí.
Y bueno, pues hoy en día nos vuelve a visitar y ahora trae esta charla que lleva por título The Spectrum of Feynman Integral Geometries in QCD and Gravity. Pues muchas gracias, Roger, y adelante.
Muchas gracias. Primero de todo, me gustaría disculparme porque me he estado mudando a Michigan estas últimas semanas y no he podido preparar la charla en castellano, pero si tienen alguna duda en castellano no hay ningún problema, puedo contestar. So today I will be talking about the connections between algebraic geometries and Feynman integrals, and I will be presenting two papers given here. The first one we published in May. It is together with my supervisor, Matthias, and two members of our group. And then I will also present some work in progress with a different set of collaborators. And as Jonathan was saying, today I will present the Feynman integrals geometries that can appear in gravitational waves and in QCD. So the outline for the presentation will be the following. First of all, I will review the scattering amplitudes and Feynman integrals that can appear for precision physics, and then I will introduce this connection to algebraic geometries. Then we will consider two different applications. In the paper that we had in May, we classified the geometries for gravitational wave physics. We will see the geometries that can appear at for loops where Calabi-Yaus occur. And then as a second application, we will consider instead the geometries that can appear in quantum field theory at two loops. This includes in QCD or the standard model. And for that, we will consider integrals in the 't-Veltman scheme, where we will see these geometries at two loops. So let's begin with the introduction. The motivation behind most high-energy theory computations is to provide precise theoretical predictions that can be later contrasted with experiments. We will be using quantum field theory, and in particular scattering amplitudes, to compute these theoretical predictions. Traditionally, scattering amplitudes were developed for collider physics, but in the last decade, 15 years, there's been an amount of work in using scattering amplitudes also for gravitational wave physics. So let's focus first on the application for collider physics. In this case, we want to study particle collisions. For example, here we have an event at the LHC where two protons were collided and then led to a shower of particles. In this case, the observable that we are interested in is the cross-section. And in fact, in experiments such as ATLAS, we now have access to 15 orders of magnitude in the energy for the cross-section. And as you can see, the agreement between theory, given in gray, and the different experiments is very precise. They almost lay one on top of the other. This is very useful and very important, for example, to test the accuracy of the standard model. And from that, we can, for example, study the properties of the Higgs boson, study its interactions but we can go beyond and, for example, probe extensions beyond the standard model, as well as even some dark matter models. So the cross-section is computed as an integral over the phase space times the scattering amplitude squared. Then in perturbation theory, we expand in terms of the coupling constant, and then in this series, we will have different corrections. The leading order correction is given by scattering amplitudes at tree level, for example, this diagram here. And when we compute these corrections, we get a result which has about 50 to 100% uncertainty. If we want to reduce the error, we have to compute a more precise correction. Then we need one-loop diagrams, such as the ones here, as well as tree-level diagrams with real emission. And then we reduce the error to about 10 to 30%. Similarly, we can go to the next order, where we will have two-loop diagrams, and then we reduce the error to about 5%. Importantly, if we want to reach a precision of about 1% uncertainty, we need to go to next to leading order. And this is important because this is precisely the error needed in order to compare with future experiments, such as the high luminosity phase of the LHC, which will become operative around 2030. And so to reach this precision, we need to compute diagrams, such as the ones here, which are at 3-loop. And as we will see later on, these diagrams become extremely difficult to calculate. This is due to many different reasons, but today we will focus on one of them, which is the presence of non-trivial geometries. So this is the familiar story for collider physics. Now, what we want is to also consider the case of gravitational waves. So in this case, we don't want to study collisions of particles. We now are interested in a binary system of astrophysical compact objects, which can be black holes or neutron stars. These objects are bound in a binary system. They are orbiting around each other, and when they do so, they produce gravitational waves. Then, in experiments at the Earth, we measure the strain, which is the relative variation in the size of the arms of the interferometer. And experimentally, this variation is very small. It can be 1,000 times smaller than the size of a proton. Still, in 2015, the gravitational waves were first discovered, as shown in these plots here. And since then, experiments such as LIGO, LIGO, Virgo, and CAGRA have detected more than 100 events. So now we have gravitational waves emitted from binary systems of black holes up to 100 solar masses. We also have binary systems with one black hole and one neutron star, and even binary systems of 2 neutron stars. This is, in this case, important because we can study the properties, origin, abundance of black holes in the universe. Similarly, for neutron stars, we can access the equation of state, but also it gives us an opportunity to study the strong gravitational regime, which allows us to test general relativity and even extensions beyond general relativity. So we will be interested in the coalescence of these objects, where we can distinguish 3 different phases. First of all, we have the in-spiral, where the objects are just orbiting around each other. They are far away from each other. Then, as they radiate energy in terms of gravitational waves, they get closer and closer, and we have the merger. Finally, this composite object settles down into a single black hole through the so-called ring-down modes. Today, we will be interested in the in-spiral, since it is amenable to perturbation theory techniques. In fact, depending on the configuration of the in-spiral, we can have different techniques at our disposal. If the distance between the objects is very large, we can use the so-called post-Newtonian expansion. So here we assume the gravitational field to be weak, as well as having small velocities. And in fact, this is the main expansion used to produce templates for gravitational wave experiments. Then, as the objects get closer and closer, at some point, strong gravitational fields will come into play, and then we have to resort to numerical relativity. Today's focus, however, will be on a different expansion known as the post-Minkowskian expansion. Here we still assume the gravitational fields to be weak, but we take into account relativistic effects. This is important, for example, when we have orbits with high eccentricity, in which case, when the objects get very close, they actually reach relativistic velocities. Similarly, since we are effectively resumming infinitely many post-Newtonian corrections, since we take into account all orders in the velocity, post-Minkowskian calculations actually complement and improve those from the post-Newtonian theory. Moreover, since we are taking relativistic corrections into account, we can use quantum field theory and concretely scattering amplitudes. And so we are able to borrow the tools developed from collider physics and use them for gravitational wave physics. So let's make this connection a bit more clear. We have this binary system of black holes. When they are very far away from each other, we can regard the black holes as being point particles, and so we can model them by just massive scalars. Then if we want to take into account other effects, such as finite size effects, tidal deformations, spin, we can do so as operators in an effective field theory, and so we can take also those into account. Now we have this binary system of point particles. What we can do is relate it to the unbound system through analytic continuation. And then the unbound system is related to the scattering process. And so, in practice, we can compute the scattering amplitude for two massive scalars which interact gravitationally. These scalars will model the black holes. And then, through analytic continuation and the effective one-body formalism, we can actually get corrections to the potential in this bound system. And specifically, via scattering amplitudes, we get these coefficients here. And then it's just a matter of computing scattering amplitudes. In the diagrams in the post-Minkowskian expansion, the thick lines on top and on the bottom, this will denote the black holes. And then these thin lines in the middle, those will represent the massless gravitons. And for example, at order g squared, we have this correction known as the 2 p.m. order. This was already calculated in the 80s, where you need to compute these 4 one-loop diagrams. Similarly, we can make this correction more precise. This was done in 2019, where we compute 2-loop diagrams such as the ones given here. Then a couple of years later, the 3-loop correction was computed. And nowadays, the state of the art is at order g to the 5. This is the so-called 5 p.m. correction, where we need to compute 4-loop diagrams, such as the ones here. The full 5 p.m. computation is still not complete. There are some partial results in the literature in these papers here, as we will see later on. The problem with this computation is that, again, computing these diagrams is extremely difficult. And so we are reaching a point in our computations where it's very difficult to proceed to the next order. By contrast, from the experimental side, we have that the 3rd generation of gravitational wave detectors will become operative around 2035, if we compare the sensitivity of advanced LIGO, here in gray, with the projected sensitivity for future experiments, such as the Cosmic Explorer or Einstein telescope, we see an improvement by 2 orders of magnitude. This means that we may require to compute even higher PM orders to compare theory with these future experiments. And so, both for collider physics and for gravitational wave physics, we need to calculate these complicated high-loop integrals in order to get these precision predictions. But how do we actually compute scattering amplitudes? You can go to your favorite textbook, Peskin and Schroeder, and it will tell you that we start from quantum field theory. You get your Lagrangian, you derive the Feynman rules, and then you sum over all the different diagrams. Once you do that, you obtain a set of master integrals, and you just have to integrate. However, this is not so simple. And for example, focusing just on the integrand and trying to calculate that one can be an entire project on its own. Nowadays, there exist many tools that facilitate getting the integrand. For example, we have BCFW, recursion relations, double copy, which relates gauge theory to gravity. We have generalized unitarity, which allows us to use tree-level results for loop-level integrands. And so getting the integrand is actually pretty straightforward. The problem is that this integrand may contain thousands or even millions of terms, so we want to decompose it into building blocks. These building blocks are the so-called master integrals, and they are the smallest independent set of Feynman integrals that we need to compute. Once we compute these master integrals, the entire result will be very easy to compute. The problem is that to get this set of master integrals, we need to solve the integration by part identities that Feynman integrals satisfy. And in current applications, this is actually a big bottleneck. This is very easy to do, but it requires lots of hours of computation in a computer. And so this is the step in this process which takes the most time. Still, today we will assume that all of this process has been carried out, and the only step that remains is the very last one, which is to evaluate these master integrals. But to see why this last step is fundamentally more difficult, let's see which type of functions we can get when we actually do these integrals. So for that, we will consider a very simple example. We have two Feynman parameters, x1 and x2, and then we take a very simple case where we have a denominator, x1 squared minus a polynomial that depends on x2. If we now integrate over x1, we get the following result, where we have a logarithm and a denominator, which both depend on the square root of this polynomial. Then the question would be, which type of functions can appear when we actually evaluate this last integral? As it turns out, the answer to this question is given by this equation here. We can define y squared to be equal to this polynomial. Then the square root is equal to y. This equation defines an algebraic curve, and then depending on the curve that we will have different geometries, and then we will have different functions here in the result. For example, the simplest case is when the degree of the polynomial is less or equal than 2. Then we can always rationalize this square root and write the result of this integral in terms of multiple polylogarithms. Multiple polylogs are iterated integrals given here. They are basically iterated integrals over this Riemann sphere. And so in this case, the degree is less or equal than 2. The geometry is the Riemann sphere, just a ball. And then the corresponding function space are just integrals over this geometry. This, for example, happens for this one-loop diagram called the bubble, as well as for this one-loop diagram called the box. And in fact, all one-loop Feynman integrals can be written in terms of multiple polylogs. When we go to higher loops, most integrals can still be written in terms of multiple polylogs. However, there are also cases which are more complicated. This starts to happen when the degree of the polynomial is greater or equal than 3. Then we can no longer rationalize this square root and write the result in terms of multiple polylogs. And this is because we precisely have a non-trivial geometry. The simplest case is when the degree is 3 or 4. Then this equation defines an elliptic curve, and the corresponding geometry is a torus, which is basically a donut. Then the functions that we get here as a result will contain elliptic integrals, but in general they are iterated integrals over this torus, which gives rise to these so-called elliptic multiple polylogarithms. There are plenty of Feynman integrals which depend on elliptic multiple polylogs. For example, this two-loop sunrise. This is the most well-known case. It was already studied in the 60s when people computed the electron self-energy in QED at two loops. However, the analytic result for the self-energy was not known until more than 50 years after. And this is precisely because of the elliptic curve in this integral, which makes it very complicated. Similarly, we have other cases. For example, this massless double box integral. This is the first elliptic contribution to n equals 4 super Yang-Mills theory. But of course, we can have more complicated geometries. For example, if the degree is 5 or 6, then this equation defines a hyperelliptic curve. The corresponding geometry is a surface of genus 2, basically a donut with two holes. And then the corresponding function space are just iterated integrals over this geometry. These are known as higher genus multiple polylogs, and they have been very recently constructed in the literature. For example, a case of a Feynman integral which depends on a hyperelliptic curve of genus 2 is this non-planar double box given here. And then, of course, if we have higher and higher degree polynomials, we will have higher and higher genus curves. However, this is the analysis for the case when we only have two Feynman parameters. So let's take the general case where we have n. Then we take our denominator to depend on the remaining variables. When we integrate over x1, we basically get the same result as before. However, this equation no longer defines an algebraic curve, but an n-1 dimensional manifold. And this manifold is such that if the degree of this polynomial is equal to 2 times n, then we have a Calabi-Yau n-1 fold. The Calabi-Yau manifolds are these very abstract geometries, usually drawn like this, but I like to think of them as being related to one of these sponges. In the literature, there are plenty of Feynman integrals which depend on Calabi-Yaus. For example, if we keep on adding loops to the sunrise, we get this so-called banana family of Feynman integrals, which depend on a Calabi-Yau L-1 fold at L loops. Similarly, we can keep on adding boxes. We get the so-called train tracks family, which also depends on a Calabi-Yau L-1 fold. But there are more complicated cases. For example, this non-planar family of integrals. These are known as the tardigrades because they look like this animal here. They depend on a Calabi-Yau 2L-2 fold at L loops. But now the question is, if we are given a Feynman integral, how do we know if it actually depends on a non-trivial geometry before doing the actual calculation? And this is precisely where my work has been focused on, to develop tools to detect these geometries before doing any calculation. So if we want to detect these geometries, we actually have two methods at our disposal. The first method is based on computing the Picard-Fuchs operator. So if you remember, we had this vector of master integrals. These are the smallest independent set of Feynman integrals that we need to calculate. If we take a derivative with respect to the kinematics, we get a system of first-order differential equations, where here A is a matrix. Then from this system, we can take more derivatives and derive a single higher-order differential equation for each of the master integrals. The corresponding differential operator is known as the Picard-Fuchs, and when it acts onto the integral, it gives an inhomogeneity. As it turns out, the Picard-Fuchs is very useful for detecting geometries, because if it factorizes into a product of operators of order 1, then we have the Riemann sphere. Instead, if the factorization involves a higher order differential operator, then it indicates that we have a non-trivial geometry. And although this process is very useful and very straightforward, there is one problem, which is that we need to get this initial vector of master integrals. And if you remember, to get the master integrals, we need to solve the integration by parts identities, which is computationally very expensive. So today we will take an alternative approach, which is based on analyzing the leading singularities. The leading singularities can be understood as the maximal codimension residue. And for example, in the case that we had before, the leading singularity here would correspond to the residue at the point where this denominator vanishes. So for example, we can compute the residue with respect to x1. Then we will get the square root of p, which you remember we denoted as y, and then this would be the result for the leading singularity. Importantly, as we see, the leading singularity captures precisely the square root of the polynomial, which was giving us the geometry. And this is because the leading singularity is a solution to this Picard-Fuchs operator here. So for example, if our geometry was the Riemann sphere, then the Picard-Fuchs would factorize, and all the results for the leading singularity would just be constants of the kinematics. Instead, if the geometry was non-trivial, then we have a higher order differential operator, and the corresponding leading singularity would be an integral over the corresponding polynomial. And so by computing the leading singularity, we can actually get a notion of the geometry that we have in our integral. The advantage is that case by case, this is very easy to compute. And in fact, all of this effort is not in vain. We can also use leading singularities to actually solve these differential equations here. And so from the leading singularity, we can actually facilitate evaluating the master integrals and then getting our observables. In our case, we compute the leading singularities through the so-called Bykov representation. Today, I will not be giving details on the Bykov representation as it is quite technical, but I am very happy to answer questions on the Bykov representation if you have any doubts at the end. So with this, we have all the tools that we need to go on and classify the geometries that can appear in different processes. So as a first application, let us look at the geometries that can appear in the post-Minkowskian expansion for gravitational wave physics. If you remember, at the end of the day, we are looking at this bound system or this binary system of two black holes. This is a very classical system. So we want to take the angular momentum to be large. As shown in this paper here, at the level of the scattering amplitudes, this means that q squared, which is the momentum transfer, is actually small. This is the so-called soft expansion. And under the soft expansion, we actually have that the matter propagators, so the black hole propagators in the diagrams, become linearized. So for gravitons, we have the usual quadratic propagators, but with the soft expansion, the propagators of the black holes become linearized at leading order, and this is actually very important. As we showed in this paper last year, having linearized propagators actually imposes many relations among leading singularities. For example, we have that the leading singularity of such diagram is actually related to the leading singularity of this planar diagram where we exchange the vertices. What this is telling us is that the geometry of this non-planar diagram, where these vertices are crossed, is actually the same as the geometry of this diagram, which is very different. And in fact, this is telling us that the functions that we get when we evaluate these integrals are actually the same. Similarly, we have other relations. For example, we have this reduction for superclassical diagrams. Superclassical diagrams are those where we have an isolated graviton line connecting the two black hole lines. And when we compute the leading singularity, we can actually remove this propagator and relate it to a lower loop leading singularity, where this prefactor here just depends on the kinematics. Finally, we also found that there are diagrams which contain this type of subgraphs which actually have zero master integrals. This means that they can be totally reduced in terms of subsectors, and so they can be dropped from our analysis. But to see why all of this is important, let's maybe do an example. So imagine that we want to compute gravitational wave observables at 3 p.m. order. Then we need to compute 25 two-loop integrals. They are all drawn here. Then the idea would be, can we actually know which of these integrals will contain a non-trivial geometry? Well, first of all, we can remove this diagram. This is because this is just the product of two different one-loop triangles. We know that all one-loop Feynman integrals can be written in terms of multiple polylogs, and so this will just be the product of multiple polylogs. But similarly, for the purpose of characterizing the geometries, we can remove these four diagrams precisely because their geometry, if we exchange these vertices here, is actually the same as the geometry above. And so let's remove those. But now we can apply order rules. For example, we know that diagrams containing this type of bubble graphs, where we have at least one vertex being cubic, they actually have zero master integrals. This means that they are expressed in terms of a linear combination of other diagrams already in this list, or which do not contribute in the classical limit. In fact, we can remove all of these diagrams where we use that this type of bubbles have zero master integrals, but also that we can exchange the vertices of the matter lines. So we can remove all of those. Then similarly, we can apply these rules for diagrams that have this type of triangle subgraphs to remove these three ones. And similarly, we know that the leading singularity of these diagrams is related to a one-loop leading singularity, since we can remove this edge here. we know that one loop leading singularities are polylogarithmic, and so these diagrams are also polylogarithmic. And so without doing any calculation, we know that if there appear non-trivial geometries, they will be totally characterized by these 4 diagrams at 2 loops. And so now the task would be to actually compute the leading singularity for each of these diagrams to see if there are indeed geometries or not. We actually did the same analysis up to 4 loops. We initially obtained more than 16,000 diagrams, and using the same rules as we saw in the previous slides, we can actually reduce it to just 70. And so now the idea would be to compute the leading singularity for each of these 70 integrals to see what geometries we can have. What we found was that up to 2 loops, all the diagrams depend on the Riemann sphere, so they are all polylogarithmic, and then the first non-trivial case appears at 3 loops. In this case, there is a leading singularity for this diagram, which is a twofold integral over the square root of a degree 6 polynomial, which satisfies the Calabi-Yau condition we saw at the beginning, and it is indeed a Calabi-Yau twofold, which is also known as a K3 surface. In fact, this diagram was already known to depend on a K3 surface, but it was very nice to reproduce it from our analysis. Then with this, we matched all the results that were known up to 3 loops, and then we started exploring what happened at 4 loops. At 4 loops, we had one surprise, which is that this diagram has a leading singularity that depends on the square root of a degree 8 polynomial. And now this defines a Calabi-Yau threefold. And in fact, this was the first time that a Calabi-Yau threefold was found in gravitational wave physics. Shortly after our discovery, there was a second diagram, given here, which was found to depend on another Calabi-Yau. And since then, more diagrams have been found. In this paper in May, we actually finished the classification at 4 loops. And what we found was that in total, there are 8 different diagrams. We have these 2 which depend on different Calabi-Yaus, and then we have 6 diagrams which depend on a K3 surface. And in fact, we were able to see that the K3 surface is actually the same as it appeared at 3 loops for 5 of these diagrams. So this means that the function space will actually be the same. So now the idea would be to use this knowledge from the leading singularities to facilitate solving the master integrals to then get the results, for example, for the gravitational wave observables. But first, we would need to compute these master integrals. So one way to evaluate them is to start from the differential equation system. Here, this matrix A can depend on the kinematics as well as the dimensional regularization parameter epsilon. And then one way to solve the system is to change bases to a new system, to a new set of master integrals J, such that the dependence on epsilon actually only appears in the prefactor. This is the so-called epsilon factorized form. And when we have this type of equation, solving for the master integrals can always be done very easily, order by order in epsilon. And then, as shown in these papers, we can use the knowledge of leading singularities to facilitate finding this transformation to get the epsilon factorized form. And this is precisely what people have been doing over the last years to evaluate these master integrals at 4 loops to compute the observables. What we can do to facilitate this task is to expand the observables in the self-force limit, where one of the masses of the black holes is heavier than the other. And then we will have 2 different contributions. We have the 1SF order. Here, these 4 diagrams, depending on non-trivial geometries, will contribute. In this case, This is already computed. It was done in this paper last year by the group in Berlin. And what they found is actually that this Calabi-Yau contributes to the final result. And this is actually the first time in history that there is an observable in nature that receives contributions from a Calabi-Yau. So now what remains is to compute the 2SF corrections, where we will have the contribution from these diagrams here. We see our Calabi-Yau as well as a different K3 surface. This is still work to be done. However, last week there was a paper by the group at the UCLA where they computed some partial results in supergravity, which seems to suggest that the contribution from these geometries actually cancels. So it would be very interesting to see if the same happens in general relativity, and if it is indeed the case, to try to predict why these cancellations occur. So with this, I finished the first application. Now, in the last 5-10 minutes, let me explain the second application, which is to classify the geometries at two loops in any quantum field theory. This includes in QCD and in standard model. So now the focus will be two-loop integrals with generic masses and momenta. Before, we were able to go to 4 loops because we had the post-Minkowskian expansion. But now, since we have generic masses and momenta, it will be more complicated. So we are doing the analysis at 2 loops. To regularize the divergences, we will take integrals in the 't-Velman scheme. This means that internal loop momenta will be considered in 4 minus 2 epsilon dimensions. This is the same as in dimensional regularization. But we take the external momenta to lay strictly in 4 dimensions. The advantage is that this places an upper bound on the number of diagrams, as shown in this paper by some of my collaborators. But to see why this is the case, let me introduce a bit of notation. So the 2-loop diagrams that we will be interested in, they can all be drawn like this. We have 2 vertices here given in blue, where 3 internal propagators meet. We can connect these vertices with 3 different paths. Each one will have a different number of propagators, in this case, A, B, and C. For example, we call this integral 3, 1, 2 because there are 3 propagators, 1 and 2, and this one is called the 3, 2, 3. Now the idea is that since we have external momenta in 4 dimensions, there can be at most 4 independent momenta, which places a bound in the number of propagators that we can have. For each of the paths, we can have between 1 and 5 propagators. If we had 0, then the diagram would factorize, and then it's a product of 1-loop diagrams, which we know are polylogarithmic, so they are not interesting. And then the total number of propagators is bounded by 11. And so with this, we have a finite number of diagrams at 2 loops. In total, we have 84. These are the 84 diagrams that we can have at 2 loops in the 't-Velman scheme. Now the task would be to actually compute the leading singularity for each one of them to see the corresponding geometries and functions. However, we actually don't need to compute the leading singularity for all of them. There are 5 diagrams which reduce to a linear combination of other diagrams in this list. So we can drop these 5 diagrams and only compute 79. And this is precisely what I've been working on in this work in progress with my collaborators to compute the leading singularities for all of these diagrams. What we found was that 54 of them have an algebraic leading singularity, so they are all polylogarithmic, while the rest of these diagrams will depend on non-trivial geometries. So, for example, overall, we find 17 different elliptic curves. This happens for all of these diagrams, we see some of the diagrams that we already saw in the introduction. The tulip sunrise on the left. Here on the right, we have the tulip double box, as well as some other non-planar diagrams. Importantly, this will be the only planar diagrams in the following slides. And so this means that if we are computing observables in planar theory at tulips, the most complicated geometry that you can have is actually an elliptic curve. But then we also have more complicated geometries for non-planar diagrams. For example, we find two different K3 surfaces. This happens for these two diagrams, which are actually the 4 and 5 point tardigrade. So this was not very surprising because we already saw those in the introduction. But then we can have more geometries. We find one diagram which depends on a genus 2 curve. This is the case for this non-planar double box, which we also saw in the introduction. Let me say that most of these diagrams were known only in certain equal mass or massless limits, but now we have done the full analysis for generic kinematics. So they still depend on the same geometry. But we can have more complicated things. We actually find two diagrams that depend on a genus 3 curve. This is the 5 and 6 point non-planar double box. And lastly, we have one surprise, which is a new geometry. So there is one diagram given here, which when you compute the leading singularity, you get a twofold integral over a polynomial of degree 4. If it was degree 6, it would be a K3 surface, but since it is degree 4, it corresponds to a Del Pezzo surface. A Del Pezzo surface is a particular type of geometry, which is actually the first time that it appears on Feynman integrals. Del Pezzo surfaces are known to be rationalizable. This can be found, for example, in this paper by Joseph Shisho. And when you do the rationalization, you get a twofold integral over a polynomial of degree 6, now without the square root. And then the leading singularity corresponds to the vanishing locus of this polynomial, which gives us a curve of genus 3. So even though we have this Del Pezzo surface at an intermediate step, at the end we get again a curve of genus 3. However, in this case, we don't know if this curve will be hyperelliptic, so it would be very interesting to try to see what the function space at the end is. And so with this, we finished the analysis for QCD at tulips. Then the idea would be to use these results for the leading singularities that we have computed to facilitate solving the master integrals through the differential equations method, and then afterwards to actually evaluate observables, for example, the cross section. So let me conclude. We have seen that non-trivial geometries appear in Feynman integrals, both for collider physics and for gravitational wave physics. We have seen in the post-Minkowskian expansion in gravity that up to 4 loops there can be K3 surfaces and Calabi-Yau threefolds. Similarly, for QCD, we have seen that to 2 loops with generic kinematics we can have elliptic curves, K3 surfaces, genus 2, genus 3 hyperelliptic curves, and even a new geometry which is known as a Del Pezzo surface. As future directions, I think it would be very interesting to try to do concrete applications to phenomenology. For example, we can take a process that will be relevant for the high luminosity phase of the LHC. These are given in the Lesuish wish list, and try to specify the kinematics to that process to see which of the geometries appears. Then the idea would be to use this knowledge to derive an epsilon factorized differential equation and then compute the corresponding cross-section. We also saw in gravity that there can be cancellations of geometries and special functions in the result, so it would be very interesting to develop tools to predict these cancellations. And then finally, it would be very intriguing to do the same classification at higher loops. Thank you very much for your attention.
Here we are. So thank you, Dr. Roger, for this amazing talk. So can we pass to the question section to the students present here? Come on, guys. Approach to the computer.
Hello.
Hello.
Okay. I have a question about being honest, I don't understand a lot, but what I want to ask is about if this, I read a little bit about positive geometry and I don't know if this is related to. So can you explain? Okay.
It's a very good question. So we actually don't know if these geometries could be related. So, for example, the positive geometries that you mentioned, they are related to the integrand. However, what we see is that the geometries here, they appear when we actually evaluate the integrals. So it is still not known what the origin of the relations is, but it could be that they are related. We still don't know.
Okay, because well, at least what I could see is that Calabi-Yau reminds me of string amplitude, so I think that maybe it will be about positive geometry.
Well, more than the Calabi-Yaus, I would say maybe the higher genus. So in string theory, when you compute amplitudes, you have a genus expansion where you will have the Riemann sphere, then you will have the torus, the genus 3, genus 4, and so on. So I could see those geometries coming from string theory. For the Calabi-Yaus, it's mostly when you actually compactify the space in string theory. So the relation is not so clear to me.
Okay. Another question.
Yeah.
You mentioned that for external particles, you choose the dimension of the external particles to be t equal to 4.
Yep.
That reminds me on shell particles. So I wanted to ask if you can you can relate these results to generalize unitarity.
So when you mean that the particles are on shell, that means that the p squared, your momenta, will equal the mass squared. However, what we are doing here is stay off shell. So we will take the momenta to be in 4 dimensions, but we will not take it to be equal to the mass squared. If we were doing so, then we would be, in most cases, in a special point where some of these integrals are divergent.
Okay.
So you will have to regularize, and then to avoid these problems, we consider generic masses and momenta.
Okay. Yeah, I don't know. Well, I think that this is an idea. Well, when you are on shell, basically the propagator stays in one point.
Yeah.
But when you are not on shell, you move the propagator, which is, well, you move the singularity of the propagator. And I think that you use that in the soft expansion. I don't know. I don't remember what.
So, for example, when we compute leading singularities, we take these residues of the integrand, but most of these residues actually correspond to taking propagators on shell. If you only take a couple of propagators, then you are doing this generalized unitarity where you join the diagrams together. But if you take all of your propagators on shell at the same time, then you are computing the leading singularity.
Okay. Thanks.
No, thank you.
More questions, guys? Here or online?
Yes, I have one.
Go ahead, Jonathan.
Thank you, Roger, for your nice talk. And you mentioned something about BCFW.
Yep.
Can you tell us a little more on how to use BCFW recursion relations for loops? What are the advantage or disadvantage? Because sounds similar to neutrality codes. No?
Yeah.
What
So
is the difference?
from BCFW, what you are doing is basically put together different pieces of an amplitude to compute another one. The problem, well, it's in most cases it's not a problem, but to use BCFW, you need to go to a particular residue, and your amplitudes can actually have contributions from the arc at infinity. So you are doing like a Cauchy theorem, you are doing a closed integral, and there can be cases where these contributions at infinity are not zero, and then it's not easy to compute through BCFW. Instead, generalized unitarity, what you do is go on shell, and then you compute the integrand, so this part here, from tree-level diagrams. So BCFW, I don't know the status at loop level, but normally what it does is put together two different pieces to get the integrand. With generalized unitarity, you can cut your diagram in as many ways as you want, and then put all of these pieces together to get the integrand.
Okay. Okay. But you can do it for any loops, or there is a limit?
I think you can do it in as many loops as you want.
Okay. For both BCFW and
BCFW, I'm not sure. I'm not sure if it's been proven for higher loops or if it's only been conjectured. At tree level, for sure, but at loop level, I'm not sure. Yeah.
Okay. And what about double copying?
Double copy, more of the same. So at tree level, it's been proven. Then at each loop order, it has been studied in specific cases. There are some conjectures to double copy at high loops. There was a paper by SB and collaborators, I think, last year, where they found a way to constructively produce integrands in gravity through double copy. But I believe that an all-loop formula is still not known.
Okay. Yeah, and you mentioned something about supergravity, but what theory?
What, sorry? Can you say that again?
About supergravity, you mentioned.
Yeah. So let me go to that slide here. Yeah. So in this paper, well, normally, for example, in this paper here, by the group in Berlin, you want to compute observables in general relativity, such that you can actually compare to actual experiments such as LIGO and Virgo. However, in supergravity, what you find is that the integrals are a bit simpler, and so this facilitates doing some of the computations. And what they actually found here is that in n equals 8 supergravity, these contributions cancel.
Okay. About it is supergravity n equal 8.
Yeah, n equals 8.
Equal 8. Okay. Yeah, because I am interested in n equal 1. So I.
No, precisely they take n equals 8, so maximal supergravity, because it will be the one that will have the simplest integrals. And at the same time, there will be limits of the results in general relativity, which are actually the same as in supergravity. So they can also do like an independent check of the results.
Okay. Thank you, Roger.
No, thank you.
More questions?
Okay. Questions here? It seems that no more questions. So thank you, Dr. Roger, again for this amazing talk.